let's move to the next question. The third one, I just pasted on the chat. So you have argued that simplest merge or just merging capitals is the basic computational operation. Could you please explain how it derives the notion of chain, a collection of occurrences? More particularly, how is the copy repetition distinction captured in the current system?
Well, when you say current system, it means whose current system? A lot of differences. So there is kind of, from my own point of view, there's, for anybody who's working in the field, current system is an evolving notion. Today's current system is improved over yesterday's. So there's no fixed current system. If you want my own view, it's partially in print, not completely. There are no, first of all, there's no question about occurrences. We don't have to worry about them. There are just basically inscriptions. Each element in the computational system is its own occurrence. There's no others. There are relations among them. Some of these relations are copy relations, but that doesn't mean they're different. But that we don't have to talk about occurrences. Just it's like saying one thing's bigger than another. There's a relation between them. So we can drop the notion occurrence, which is pretty complicated notion, so it's nice to drop it. Everything, every inscription is its own occurrence. And for those of you who are familiar with the logical tradition, this is basically what was called nominalistic logic. Each thing is itself and nothing else. Then the question is, what about copies and repetitions? Well, there's been a long study of this question. It's been convoluted. There's papers like some of you have seen the Collins-Grote paper, which shows many complications in trying to define it. I think we can solve all of that very easily. It's been looked at the wrong way. The problem has always been assumed to be, why are there copies? And how do we form copies? Actually, it's the other way around. Copies come automatically in any computational system. The problem is, why are there repetitions, non-copies? So suppose you're doing, let's take a computational system that's pretty close to language, maybe the closest analog we can think of in formal logic, formal systems, namely the rules, developing the rules of formation for some formal system. So suppose you're studying, it's your first semester in logic. As a freshman, you're studying propositional calculus. You can form P, not P, P or not P, not P or not P. These are, you start with the primitives, P, Q, and so on. You have operations like negation, disjunction. You can keep applying these one after the other. You get more complex expressions by applying the rules of formation. Now, there's an assumption that is so obvious that nobody even bothers to state it, but it makes a difference for us, so let's state it. Assumption is what we might call stability. If a symbol appears at a particular line of a derivation, then it has, and at some later line of the derivation, they have to be absolutely identical. You can't change the interpretation of a symbol in different lines of a derivation. If you're constructing a proof, let's say, and you have a symbol 0 at one line of the derivation of the proof, then at a later line of the proof, you have the symbol 0, and you interpret it as the least thing possible, the limit. That's an invalid proof. Actually, this is a major issue in the history of mathematics. There's a long debate for centuries now about whether Isaac Newton's proofs were actually valid. There was no theory of limits at that time. And there's been claims that at certain points in his proof, 0 is 0, and at a later point, it's as small as possible. which would make the proof invalid. You have to have a pure identity all the way through a proof or a derivation of formal systems, or for us, generation of language. So we can simply take that property of stability over, simply a property of computational systems, which means if you say do internal merge, you take an element in one position and you merge it to the unit that it's part of. The two things that are formed are just automatically copies, nothing further to say. That's just the nature of computation. Interesting questions arise when you look at external merge. There's stuff in the literature about it, but I won't go into it. But any operation that forms new things they're always identical to what they were before. That's computation. Now there's another notion which has to do with language. You don't have it in formal systems. There's very good reason to believe that for language, not for formal systems in general, language follows general principles of computational efficiency. Humans are an organic system. The brain is trying to do things as simply as possible, least work possible. That's why you have principles like the no tampering principle, which simply says, don't toss in bells and whistles that aren't needed, okay? It's a general property of computation in organic systems that they're trying to maximize efficiency, do as little work as they have to. That's different from, say, a proof where you don't care. You don't have any limitations on memory or anything else. Anything done in the formal sciences, you just disregard this constraint. Doesn't have to be efficient, just has to work. Nature doesn't work like that. Nature is seeking the simplest thing, always, whether it's wings of birds or language or anything, or a bacterium or anything else, just general property of nature. Galileo, the way Galileo put it is, nature is simple, and it's the task of the scientist to try to show that it's simple. If it looks complicated and chaotic, you haven't done your job, because Mother Nature is trying to do things as simply as possible. That's the nature of evolution, the nature of development, and so on. That's been the driving principle of science for centuries, quite correctly. We now understand a lot about it in the biological sciences. Well, language is a biological system, so it's going to be the same. Now, what does this mean for language? Basically, what it means is one fundamental principle. When operations in generating and carrying out a derivation, we start with the lexicon, atoms, construct new things from them. The things we've constructed constitute a workspace, a set of things that you can use to move on. Okay, again, in formal systems, nobody bothers to mention this because it's too trivial, but for us, it's important. And if you want to apply an operation to elements in the workspace, you have to find them first. Okay, you want to merge two things, you have to find them somewhere in the workspace. Nature is saying, let's do it as simply as possible. Okay, we want to have what we can call optimal pairs that are optimal in that they involve least search. Well, if you look through it, you find that internal merge is the optimal pair, does the least possible search. In fact, the question for many decades, it's been assumed by me as well, that the appearance of displacement in language you hear something in one position, you interpret it somewhere else as some strange anomaly. Why should language have that crazy property? And there's been efforts to transformations, basically. Why have these things? Why not a simpler system of just merging things with what we now call external merge? That's backwards. The simplest operation is displacement, internal merge. That involves the least search. External merge involves searching the whole lexicon and everything that's already been constructed, the whole workspace. It's a huge search operation. Internal merge says take one element, look inside it, add it, merge the two. That's the most trivial operation. So the optimal construction happens to be internal merge. But for merge, the operation merge, other conditions are required. It's a constructive operation. One of them doesn't add too many new elements, what's now called research restriction. Another is it has to satisfy theta theory. That's a property of language, not of computational systems. So merge has some extra conditions. But if you just look at the pure combinatorial nature of the system, the structure of essentially minimal search, looking as finding two things that are as close as possible to each other, you can call that an optimal pair. Turns out that the actual cases of merge will be optimal pairs. But then there are other kinds of cases of optimal pairs which don't satisfy the other conditions of merge, don't satisfy theta theory, don't satisfy this resource restriction thing. So we have a general operation just looking at the computational system, which says when you have an optimal pair, assign the copy relation to it, period. Nothing more has to be said about chains. Just optimal pairs have the copy relation. That's going to include as a special case internal merge, which does satisfy the copy relation, but it also does independently just because of stability. So it seems to me that's what the general structure looks like. So there's nothing, and repetitions are just things that aren't copies. The reason you get repetitions in language, but not in formal systems, is because of theta theory. If you just use internal merge, which is the simplest operation, turns out what you get basically is arithmetic. You get the successor function and a basis for addition and so on. And in fact, that may be the reason why humans have arithmetical capacity. It's always been a kind of mystery back to Darwin and Wallace. Why do all humans have arithmetical capacity, though it's never been selected? In fact, it was never even used until very recently. For Darwin and Wallace, that was a major problem. The answer may be it's just an offshoot of language. It uses the simplest operation in language. Well, language also uses external merge because there's no other way to express argument structure. So we have to have that more complex operation available. But now if you look at optimal pairing, pure computational operation, you get optimal pairs, some of which were constructed by internal merge. That leaves a gap, the ones that weren't constructed by internal merge. And I have a paper which Angel has, maybe you've seen, which argues that several modules of language, like obligatory control, unconstrained sequences, unstructured sequences, these are just made available by the fact that that gap exists. They exploit that gap. So I think my own current view, if you want, as of today, is that that's probably the answer to the problem of copy and repetition. No problems about copies, no problems about occurrences, just a gap between optimal pairs and internal merge, which meets other conditions as a combinatorial operation. And out of that gap comes several modules of language, which it's what I've been calling all of this simply follows from the strong minimalist thesis, which is language is perfect. That sounded crazy when it was first proposed 30 years ago. To most linguists, still sounds crazy, but it pretty much has to be true. And it's one of those things that you want to show should be true. There's a pretty good reason for it. The reason has to do with the nature of human evolution, which we don't know a great deal about, but some things are known, which weren't known a couple of years ago. So it's now been shown by genomic analysis that, which is quite solid, that humans began to separate roughly 150,000 years ago, no later than that, maybe before, but at least then. And they have the same language faculty, which means that it was in place before they separated. Now, humans altogether emerged roughly 200,000, maybe a little longer, years ago. In evolutionary time, that's just the blink of an eye. It's an instant. And before humans emerged, there's nothing in the archaeological record that gives any indication of any kind of symbolic activity or complex social structures. So it's pretty reasonable to assume that language just emerged along with modern humans. But that, as I say, is an eye blink of evolutionary time, which means that what must have happened is that some small change in the brain led to recursive generation for the first time. And then Mother Nature came in with her scalpel and said, let's do it as simply as possible, just like everything else. And if it's as simple as possible, it should have the optimal conditions of efficiency for organic systems. So if you put this together, it's pretty natural to expect that we will discover sooner or later that language is perfectly designed and that the apparent complexities are either things we don't understand or else they are at the periphery of language, having to do probably with externalization. Now that's the direction in which things ought to be moving. This is heresy in most of the field, but I think that's where things are going, if you want my current theory, current opinion. Does that cover it? And yes, that also means that we really don't need the notion chain. You can define it, a chain will just be a collection of copy pairs, but the copy pairs just come from optimal search with this crucial gap between optimal search and internal merge.